Two administrative announcements as we start today. The first one, mostly aimed at Dr. Kem's lab section. In my two sections, I went over some Excel tips and tricks that will make your life, I hope, a little easier on doing the calculation, the measurement of the spring constant of that big brass spring that I stretched with some masses. Dr. Kemp said he did not do any help on Excel skills with his lab sections. I did make a video which is posted that is what I went over with my two lab sections, and so mostly for Dr. Kem's section, but anybody else who how did he do that again? How did he make that little thing work in Excel? How did he get that trend line? How did he get a slope? That it's posted on Canvas in two locations, right below all our classes. It's tucked in right after Wednesday's class. It'll be in before today's class. And also, I put it in the lab module itself at the very bottom. So if you have trouble with Excel, you can take a look at that. If that's also something perfectly fair game for office hours. I will hang around today at 9:30 for office hours, and then I'll be back again at 10:30. Sometimes I don't do that on Friday, but I have the ability. And of course, the exam is next week, so I want to make myself available to you if you need help with anything. Second point on the lab. It dawned on me that the only part of it that is relevant to the exam next week is measuring the Hooke's law spring constant. Conservation of momentum, the second part, is not on the exam, and there's no reason to distract your focus from the exam. So this week's lab, okay, lab 8, won't be due till the following Thursday. So I'll extend that out. And I just by habit made it due next Thursday, but that is, of course, the day that you'll be turning in your midterm. And so I don't want to distract you with that. Same subject. If you notice the homework for next week, normally I have homework due on Wednesday night. I move that till Friday night for exactly the same reason. There's nothing specifically on the homework that is due next week that'll be covered on the exam because it's all chapter 9. That said, though, I will tell you, there's no waste in doing the homework if you've got some time. I was working with a couple students on the conservation of angular momentum worksheet. And you remember the ice skater problem where the ice skater pulls her hands in, and you had to calculate the moment of inertia at 2 points. And a couple people went, isn't that exactly what I had to do in the rotational motion, torque, and moment of inertia lab? And that's exactly what I was supposed to do with the two masses when they moved in along that stick. And one person said, hey, I just realized probably from that worksheet, I completely was doing the lab calculations wrong. Can I have extra time to turn the lab in? And that happens in physics. As I say, it is not necessarily explicitly meant to be a review, but it often does self-review. And that was an example where conservation of angular momentum had you working with moments of inertia, which was a topic that will absolutely be on the exam. Okay, so I don't want to distract you with chapter 9 stuff. Conservation momentum won't be on the midterm next week, but at the same time, if you're working with velocities and angular velocities and masses and moments of inertia, well, that will be on the exam. And so any practice you can get is probably good, even though the specific problem might not be there. Any questions on that? All right, so those are the two modifications. I'll push the due date of the lab from this week till the week after next, and because there is no lab next week, and also the homework was already pushed from next Wednesday to next Friday night. All right, new material today. Completely new chapter 10 already. Almost hard to believe we've gotten through 10 chapters in what, 10, 11 weeks, whatever it is. We're finishing the 10th week, and that is about the pace of a course like this. It is to a great extent a survey of physics, mechanics of physics, and we'll continue on. We've got a couple more topics to talk about, but energy is the next one, and we're actually going to spend in total about 2 weeks on it. And it represents a different way of solving physics problems. We spent the first 8 or 9 weeks looking at Newton's laws. in pretty much every aspect of Newton's laws you can possibly think about. We've tried to solve a problem in that way. We've solved Newton's second law in rotational motion. We've solved Newton's second law where the acceleration was zero and things were in equilibrium. We've solved Newton's second law for translational motion. Hopefully you even understand why Newton's second law comes into play in projectile motion problems, all kinds of stuff. Last week, we took a different turn though. We realized that there are problems where Newton's second law will be problematic for us because there are forces which aren't constant. And our machinery, our mathematics, in order to do problems, is limited by the fact that we only have a set of equations if we have a constant acceleration. And in order to get a constant acceleration, Newton's second law says we need a constant force. But we introduce springs, and if you stretch the spring more, you get a bigger force. If you stretch the spring less, you get a smaller force. Depending on how much you stretch the spring, you'll have a different force. We don't have an equation for an acceleration of that type where it's variable. Okay, and that's, I only ask you questions that you have to calculate velocities and positions when you have a constant acceleration, and all of a sudden we've got a case where that's not so. Okay, as the spring pushes on something, it exerts a different force as the object moves, and that causes a different acceleration. And so our technique was momentum conservation. We would hope that we could isolate the system so that there are no external forces acting. And then if there's no external forces acting, we hope that the momentum at the start of the problem is equal to the momentum at the end of the problem. Pretty straightforward. People ask me, I don't know what equation to start with. And it's really the wrong question if that's the one you're asking. The concept is the momentum initial equal to the momentum final? And then you look at all the objects, and momentum is mass times velocity. You have to know that and say, okay, what's the momentum of that object? What's its mass times the velocity? What's the momentum of that object? I don't think we'll ever give you a problem with a third mass or a third object in it. It's possible. What's the momentum of that object? You add them all up. If they're all at rest, the initial momentum is zero. And then you figure out what the momentum is after the interaction, and you add up those momentums. And the momentum, hopefully before, is equal to the momentum after. If there's a velocity or a mass or something that you don't know, hopefully there's only one thing you don't know, one mass, one velocity. If you've got the momentum, all the other momentums before and after of all the objects in your problem, you can solve for the unknown. And that's pretty much how it works. Sometimes the objects stick together. That makes life a little easier for you because then you add masses up and they have a singular velocity and they move off together if they stick together after a collision. And so that's the kind of stuff we'll do. We will have a lab on that after the week after next. We'll collide some carts, have them stick together. Won't be on the exam, but that is a new thought on how to solve physics problems. And today we use that same idea, but now we're not going to look at momentum before and after some sort of interaction. We're going to look at energy. Okay, what's the energy of a system before some kind of interaction, a collision maybe? What's the momentum? I'm sorry, what's the energy after that interaction? And we believe in physics, in an isolated system, energy can't be created or destroyed, only moved around. Moved around amongst what? Well, the videos last night, the one in the reading quiz and the one I made, went through a whole bunch of types of energy that we consider in a physics class: chemical energy, thermal energy, energy of motion. That's the first one we care about in physics. Kinetic energy. We'll talk about that here in a second. And then we're going to talk on Monday of next week about potential energy, the ability to move, to cause motion. We refer to that as potential energy. And in this class, we're going to talk about two types. We're going to talk about gravitational potential energy and elastic potential energy. And if you come back for PHY102 in the spring, you'll learn about electrostatic potential energy. And so we believe that what happens in a problem is if you can bookkeep, literally, think of these energies as accounts in a bank. You have a checking account, a savings account, maybe you have an investment account. Think of energy as dollars in an account, and the transaction between those accounts we either refer to as work or heat. And that's what allows us to move energy between these accounts. It's a good analogy. It's the best one I got. And, we're not doing it all today. Today, we're only going to talk about one of the transactions, work, and one of the types of energy, kinetic energy. But you should understand things like heating up something takes energy that might be in a kinetic sense and transforms it via the heating up process of friction into, say, thermal energy. And you should kind of have that picture in your mind. It isn't lost. We don't believe energy is lost. It may be lost to our particular needs or our particular calculation, but it isn't lost according to the universe. I guess it's still there. All right, so that's enough of a preliminary. Let's get to the math, because I'll share this with you. It is a physics course. We are going to do math. Hopefully, yep, you're seeing my PowerPoint, and this is the big slide of the day. Let me make it a little bigger for you here. Make that a little bigger. Work. What is work? It's a definition. It's like taking a foreign language sometimes in physics or other sciences as well. You got to learn the definition of work. And this one's a little bit troublesome, I think. I've always had a little bit of difficulty with it. Work is a force times a displacement. Good to go. Okay. It has to be a force parallel to the displacement. And so that gets me this factor of cosine of theta. But if you watched the videos last night, you saw a couple interesting things, like if you're conducting a tug of war and nobody's moving, you're just straining against a motionless rope. By our definition, you're not doing any work. And anybody who's been involved in that activity knows, yeah, you are. You're sweating, you're straining, you're doing it. But by physics, in our physical world definition of work, you're not doing any. Here's another example. If you're doing an exercise that causes you to start and stop at the same place, I'm thinking like a bench press. You start with the weights up, they come down to your chest, you push them back up. What's your displacement at the end of that cycle? The answer is 0. So over one cycle, how much work have you done? The answer, technically, according to our definition, is 0. Hate that, but that's the definition. Here's one more. I showed you a picture of a guy carrying a grocery bag, and he's walking at a constant speed. He's pushing upwards on the grocery bag, but he's walking horizontally. How much work is he doing by carrying that grocery bag? Well, if you look at our definition, the angle between his displacement, horizontal, and the direction he's pushing on the grocery bag is 90 degrees. 90 degrees, the cosine in 90, hopefully he realizes 0. By definition, he's doing no work. So these are some subtle points about our definition that you just have to come to grips with. But work, force times the displacement in the direction, the force being the component in the direction that you're pulling or pushing or moving. Okay, that's the definition. The good news is once you get that, you're actually getting the component of the force in the direction of motion. That's why the angle theta is right there. Hopefully you realize that force times the cosine of theta is the component of the force along that delta x vector. Okay, as long as you can see that, that's the last time you'll have to do trigonometry right there. Okay, because energy is a scalar. The meaning of a plus and minus sign is, are you putting energy into the system? Plus, are you taking energy out of the system? Minus. And that's completely different from forces and momentums, which are vectors, where pluses and minuses denote directions. Are you going to the right? Positive, generally. Are you going to the left? Negative, generally. Are you going up? Positive. Are you going down? Negative. In forces and momentums, in vectors, we use pluses and minuses to denote direction. And I watch people hold on to negative signs, and I'm like, what's that negative sign mean to you right now? Okay, and that's an important point in a physics class. If you're working with a vector, like a force or a momentum, the negative sign or the positive sign indicates a direction. In energy, completely different meaning. It means, is the energy going into the system or is it coming out of the system? All right, today, work. You got to have that definition down. Second thing, kinetic energy. We're talking about only that piece of energy. And I scribed in my terrible penmanship with my mouse here an equation that hopefully you remember from the second week when we talked about constant acceleration. The final velocity in a direction squared is equal to the initial velocity in a direction squared plus twice the acceleration times the displacement. It's an important equation. I derived it. You can even see the derivation. It's on a sheet of paper in Canvas. If you want to see where that came from, it took our constant acceleration equations for position and velocity as a function of time and eliminated the time variable. So what we got is velocity as a function of position. A handy equation. You've used it. I want to manipulate it just a little bit. And so sorry about that. I had this saved up, so I wanted to recopy to save myself time. Watching how slow this is moving, I may not have saved any time at all. Maybe I should have just rewritten it because I want to manipulate that thing a little bit. So I'm going to put it right down here and let's get rid of all those boxes. All right. And the first thing I want to do to manipulate it is I want to multiply everything by the mass. All right, hopefully I got a template here. There we go. I'm going to multiply by a mass. Multiply by a mass. Put a little m right in there. Okay. And then the next thing I want to do is I want to divide out that 2. Divide out that 2. Okay. And hopefully, if you did the reading, looked at the videos, you realize that is the final kinetic energy. That's how we define kinetic energy. Just taking this equation with those 2 simple steps, dividing or multiplying every term by mass and then dividing everything by 2, I get final kinetic energy. It's equal to the initial kinetic energy. So we just decided, big equation for today, kinetic energy, capital K. Sometimes you'll see people write KE for kinetic energy. The energy of motion is then defined to be that quantity, 1/2 the mass times the velocity squared. Okay. But then now look what's over here. Mass, that's mass times acceleration. That's a force in the same direction as the velocity, and it's a displacement. So this guy right here, that's the work done. Okay, so what we're saying here is apparently that the difference in kinetic energy, bring the initial over to the other side of the equation, is equal to the work done. That's simple. It's called the work energy theorem. All right, that's it. Any questions on that? It's a whole new thing. So I'm giving you about a little, 18-minute soliloquy of what you have to be able to do there. And next I'm going to jump to, oops, I showed you an answer. I hate when I do that. I'm going to jump to some polling unless anybody has any questions. All right, let's see if you got it. Let's see if you got it here. Polling, go all the way down to the bottom where I stuck this one and launch it. Had a second to look at it. You know the definition of work because I just went through it. Each of the boxes pulled the same distance. Frictionless floor, which box experiences the greatest change in kinetic energy, which is another way of saying, since they're equal, which one has the greatest amount of work done. I'll put the equation up one more time. Oops, don't have a pen called up. All right, I just grabbed a pen. Listen when I do this. All right, a little slow coming in this morning. I'll clear the cobwebs, I guess. But most of the people see it. All right, I got a lot to do here today, so I'm cutting you off. It's been 1 minute, 20 seconds in poll. Let me share the results with you. D is the big answer. The distractor here is the various masses, which might cause you to think about acceleration. But remember, all boxes are pulled for the same distance. The angle between the displacement, which is presumably to the right here, and the force is 0. Cosine of 0 is just 1. So the biggest force will have the most work done. And so those of you that picked D, 16 of you, great job. That's exactly right. All right, let's move on. D. Next one. Go to the next poll. And I got different forces here, a 10 Newton, an 8 Newton, and a 6 Newton. at different angles though. Put it up again because it's new equation for the day. And I gave you a couple trig, that's supposed to be an X. There, it looks like an X. Gave you a couple trig functions there. Might help. I'm hoping you know that the cosine of 0 is 1 and the cosine of 90 is 0. It's a math fact I hope you can recall. Yeah, I know you got to do math in your head here. How many people are grabbing a calculator? I hope not many. Math isn't that hard here. All right, I got 22 in. We're going to end it. This is regrettable, but good job to the people who picked C here. Because look, this force right here, this is the guy carrying the grocery bag that I was talking about in my example. The displacement is to the right. The 10 newtons is upwards. That's a 90-degree angle. The cosine of 90 degrees is 0. Amount of work done here, 0. Start a little chart up. Over here, all right, so I got an 8 Newton force acting at a 60-degree angle. And by the way, that's a joule, which is a Newton times a meter. Let's see, 8 newtons times the cosine of 60 would be 8 times 0.5. That's 4 joules. And I guess to make this work, and I think I've told you this is my approach, if I don't know a distance and I want to get numbers, just make them all. It all says it's the same. Let's make them all the same at 1 meter. Okay. And then I guess the last one here, this would be 6 joules, wouldn't it? Because that's a 0-degree angle. The cosine of 0 is 1, so it's just 6 times 1, 6 joules. See how that works? Yeah, 6 Newton force does the most work because of that angle. Important idea. But once you're through with the angle right here, once you've got the work done, it's now a scalar. You just add energies just like you add 2 and 2 is 4. It is that simple. You never have to worry about direction again, but you got to get through this step right here. Questions on that, since a lot of people went with the 8 Newton force. I'm thinking maybe you saw that number first and you multiplied 8 by that number, and that is greater than, it'd be like 6.4, which would make that one bigger. But remember, it's the cosine that matters here. Okay, stop sharing. If I tricked you on that one, I apologize. I'm going to blame Dr. Kaiser. He actually wrote the problem, wrote the question. All right. Remember what I said about the meaning of positive and negative here. And we're split about even here. That figures. You got to let go of old ideas. Energy is a little more simple if you accept the new ideas. All right, I'm going to cut it off. Unfortunately, most people pick negative, I assume because it's going to the left. The force is certainly negative. The acceleration will probably be negative, but Robert is doing a positive amount of work. Here's how you can tell. He's pushing that way with a force in that direction. The displacement of the block is also going to be in that direction. Our work is going to be positive. Okay, he is adding energy to the system. He's doing a positive amount of work because his force and his displacement are in the same direction. Okay, by the way, what would negative work look like? What if the thing was moving that way because somebody had given it a shove and he was trying to grab it and stop it from going? So he might put a force that way to try to keep it maybe from going over the edge of a loading dock or something because it was already moving to the left. Well, now what's your angle? Your angle is 180 degrees. This is an example of negative work right here. If the displacement is that way and you're slowing it down by putting a force in the other direction, why? Because the cosine of 180 degrees, that's -1. So in our definition of work, force times the displacement times the cosine of the angle. If the force and the displacement are 180 degrees apart, you're taking work out of the system. You're slowing it down. And there's the mathematical justification for it right there. Okay. Positive and negative work, energy and work are handled differently with respect to what is the meaning of positive and negative than forces and momentums. Completely different idea. All right, moving on. 10-4. Anything else I want to say here? Yeah, I think I said both of those two things. Move on to the next one. Everybody see what happens? Initially moving at 0.5 meters per second. You stop it, it comes to rest in 1 meter. Then you speed it up again with the air back on, turn the air off. How far do you expect it to go? A couple of people see it. Most people went at the wrong point. Here's your hint. A couple more people are seeing it. This one's a little tricky. Here's your key there, right there. All right, cutting it off. Unfortunately, again, majority have the wrong understanding here. Look, what's causing the air cart to come to rest? What is the force we're talking about here? The force is friction, right? It's kinetic friction, as you recall. And if the object is moving, say, that way, the friction force is that way. It's slowing it down. Okay. So that's the work being done. Presumably, when you turn the air off, you get the same force of friction. You haven't changed the normal force at all. You haven't changed the coefficient of friction at all. Okay. So this is going to be the same. But if the velocity is doubled, that means the change here as it goes from moving to 0 is increased by a factor of 4. And so I would expect the displacement to also increase by a factor of 4. So the 6 of you that went D, you realized velocity gets doubled, but it's velocity squared at the start. It loses all of that. The force is going to be the same. This then must go up by a factor of 4 as well, because you doubled this right here and it was doubled squared. Hopefully you see that now. We'll stop sharing, move on to my last one for the day here. Yeah. Skier is gliding in. I'll be honest with you on this one. I got it wrong when I first looked at the problem. The key word here, constant speed. And most of you go in the same direction I went. All right, so I'm going to end it here real quick because got to move on to do a problem for you. Share the results. I picked B2. First time I read the problem, I didn't read it carefully enough because I'm like, yep, he's got gravitational potential energy. You saw the kangaroo dropping the ball on the video. It takes gravitational potential energy, and as the ball falls, it gets converted to kinetic energy. But here's the thing, doesn't the kinetic energy continue to cause the ball as you drop it to speed up and go faster and faster and faster before it finally hits the ground? It does. I mean, that's what we expected. We did free fall earlier in the semester. We expect that the speed will increase, that the kinetic energy will go up as the gravitational potential energy goes down. More on that on Monday. We'd expect the same thing from the skier. But the key here is that he moves down or she moves down the slope at a constant speed. So kinetic energy isn't increasing. So the potential energy is not going into kinetic energy because it's a constant speed. That's why B can't be right. So why isn't the skier speeding up as the skier goes down the slope? If you've skied, you know you do until a point, and then friction takes over. No matter how well you've waxed your skis, friction takes over. If the slope stays the same, you reach some constant value. Okay. And if you're snow plowing or swishing back and forth side to side, you're actually creating friction to slow yourself down and keep yourself at a constant speed, right? That's the whole point of skiing, to control your speed. So where's the energy going? If friction is what's causing the person to go at a constant speed, okay, it must mean that that potential energy from gravity, because the person's up at the top, must be going to friction and thermal energy. So the couple of you that picked D, you nailed it. Good job. A subtle question. And we're not going to deal much with thermal energy in this course. So we'll talk a little bit about it in the upcoming week, the week after, a little bit end of next week. I think Friday and then Monday of the following week, we'll be talking a little bit about thermal energy, heat, calorimetrics. We won't be looking much at how friction creates heat, but that is the bottom line. Atoms, molecules rubbing against each other warm up, and that's thermal energy. And that even in an ice covered mountain, that's how this works. All right. Any other questions? All right. We'll stop sharing this. I'm going to go over, I got to work a couple problem, at least one problem for you today. And then I'm going to turn you loose to do some others. May not break up into groups because it's probably just going to take too much time. Screen mirroring here, Zoom. Come on, you can do it. There it is. Get rid of that stuff. And here's my first problem. And at top of the worksheet, I've given you the formulas for today. What is kinetic energy? You know, in physics, a lot of simple three-term equations. 1/2 mv squared, the work energy theorem that we talked about, the work done changes the kinetic energy. The formal definition of work, and by the way, don't worry if you've never multiplied vectors with the dot product, but those of you that have, just as maybe a helpful way of memorizing, we are doing dot product here. That is how it's how the multiplication between a force and a displacement vector works. I've called displacement delta x here. Okay. But the bottom line for everybody else, if you don't know how to multiply vectors, it is a force times a displacement. I went with d over delta x because d starts with this displacement starts with d. Hopefully that'll help you memorize it, and cosine of theta. Okay. And then I just put that velocity final is equal to velocity initial plus twice the acceleration times the displacement equation as well. Those are the equations for today. All right. Let's turn that way. And I got a problem where I've got a cart of 4.8 kilograms rolling down a ramp. Get that out of the way. I always get these pop-ups that are absolutely irrelevant to what I'm doing at the time that just drive me nuts. Okay, so we got this ramp. Hello, welcome. I've got a cart here with, I guess, wheels. It says rolling. The angle 19 degrees, okay, of the inclined plane. A constant force is applied upwards. Okay, let me get a better looking force here. I made everything go away on me. Let's draw the ramp back. Let's draw the block. There's my force upwards. some wheels. That's my 19-degree angle. Let's see. Constant force applied directed up the ramp slows the cart down and brings it to rest over a distance of 0.46 meters. Okay, at the start, the thing is moving at 2.2 meters per second. And then, of course, down here, it comes to rest. And that's a 19-degree angle right there is what we've drawn. So that's my picture, kind of crude, but gets me through here. I want to draw a free body diagram real quick. So let's slide down here and put a free body diagram right below it. There's the force that's being applied. I'm going to subscript it now with applied. I may just drop to A here in a second. There is a normal force, right? And there is a force of gravity, a weight force pulling that way. Anybody think of another force? All right. Well, good. So I guess the first thing to do is I got to figure out what the change in kinetic energy of the cart is. And so let's look at part A here. Kinetic energy initial is equal to 1/2 the mass times the velocity initial squared. I think I have all those numbers, don't I? That's 1/2 times the mass, 0.48 kilograms, and the initial velocity was 2.2 meters per second. That's squared. And when I multiplied those out on my calculator, I got 1.16. And the answer should be joules, right? Because it's energy. That's a kilogram times a meter times another meter per second squared. So it's a force times a displacement. Sure enough, it's a joule. This pen's bothering me today. 1.16 joules. All right, there we go. What's the final kinetic energy? Now it says the car comes to rest. Comes to rest. That means its velocity is 0. Final kinetic energy is 0 joules, right? Okay, so what's the change in kinetic energy? The change in kinetic energy then is the final value minus the initial value, which is 0 joules minus 1.16 joules, which is equal to minus 1.16 joules. This block, this cart, whatever it is that's rolling down the incline, is losing energy, right? It's losing energy to the whatever is doing the work. Okay, whatever is removing it. Maybe it's somebody's hand that reaches out and grabs the thing and puts an upward force on. Maybe it's a tension in a rope that somebody grabs and starts pulling upward, takes energy away by the transaction of that work. Okay, it's not lost to the universe. The person who or the thing that is putting that force on is actually engaging in pulling up some amount of work, I guess. So that's, but it's being lost to my cart anyway. That's absolutely truth, absolute truth. All right. So the next question is how much work is being done by this force, and let's see. Work done, we said, was the change in kinetic energy. So the work done is equal to, just calculated it, 1.16 joules. And I said it being done by whatever it is that is pulling on the cart. Okay. But that thing that whoever's pulling on has to also think about, well, what's the work done by each of the forces here? Okay. Because we haven't really identified the work being done by the thing pulling the cart up the inclined plane. We got to look at all the forces in my free body diagram and figure out what the work is by each and every one of them. They must add up to be minus 1.16 joules. And so I guess the next question, what was the next question? The next question is what's the work done by gravity? Okay, well, that's an interesting thing. Remember, the displacement vector is that way, right? There's delta X or D, whatever you want to call it, is that way. And so I think if I'm trying to find the work done by gravity, and so now maybe calling that force weight is sort of a bad choice, isn't it? Let's go with force of gravity here instead, because you can see it's we're using W in multiple applications. So work done by gravity is equal to the force of gravity, the weight, times the displacement, times the cosine of the angle in between the force of gravity and the displacement. Where is that angle? It's right there. Okay, that's the angle theta we're talking about. Is it the 19-degree angle of the inclined plane? No, it's not. Okay, the angle here in this case is the complement of that. It's 90 minus 19 degrees, which I think is 71 degrees. Hopefully you can recall when we did problems before, the inclined plane angle lives right there. There's where the 19-degree angle is. The angle between the displacement and the force of gravity is 71 degrees. And so I put that in. What's the weight? The weight is the mass times the acceleration due to gravity. Okay, I've got the displacement. That's the 0.46 number, 0.46 meters. So I could just put delta x and the cosine of theta, theta being 71. Put those numbers in now. 0.48 kilograms, 9.8 meters per second squared. That hasn't changed at all. 0.46 meters is the displacement, okay? And then the cosine of 71 degrees. I do that and I get 0.704 joules, 0.704 if you like putting a preceding zero on. All right, that one took a bit of effort to get. That's probably the hardest one because it has an angle. All right, let's see, what else do I have? Next question. What is the work done by the normal force? Well, hopefully that one's obvious. The normal force is perpendicular to the direction of motion, to the displacement. The angle is 90 degrees. The cosine of 90 degrees, 0. Normal forces do no work. That's a fact. You can almost memorize that one. Normal forces can't do work. Way it is. All right, next one. What's the net force then? Okay, the net work had to be, let's see, the work done by whatever that applied force is, plus the work done by gravity, plus the work done by the normal force, well, that one's 0. And all of that has to be equal to minus 1.16 joules. Okay, well, we know what this is. And so we can figure out what the work done by the applied force is. And that's the argument. The net work done, which we know because it changed the kinetic energy, has to be equal to the sum of the work done by all the forces. All right, so that tells me that the work done by the applied force is equal to, let's see, minus 1.16 joules. And then I'm going to put the 0.704 joules. I guess I have to subtract it as well. And that must be that the work done by the applied force is, I add those two together, but they're both negative, minus 1.86 joules. Okay, now I think I've answered E. What's the work done by the applied force? From the knowledge of the work done by the other three forces in the problem, then the last question is, well, how big is that applied force? And that applied force times the displacement, I'll call it D here, times the cosine of the angle in between the displacement and the applied force. By the way, that's 180 degrees. So that's just minus 1, has to be equal to 1.86 joules, the work done by the applied force. And so in order to find that force from the applied force, the force of the tension or somebody pulling on it, whatever it is, I just take minus 1.86 joules and I divide through by the displacement, 0.46 meters, and the fact that the cosine of 180 degrees is minus 1. And sure enough, I get that force that I need. It's now a positive force, positive 4.06. So about 4.1 is probably the right answer here. A joule divided by a meter is a Newton. The reason it's positive is because the cosine of 180 degrees is minus 1, and the net work was minus 1.16, and then gravity had to be up, had to be pushed, had to be pulled against as well. So there was an awful lot of work that had to be done by that person pulling up the inclined plane, which if you ever tried to do, you've experienced it. It is a lot of force that you have to apply. And so that's the answer. Any questions on that? All right, well, I got two for you, but we're gonna hold on one. We'll wait till Monday for the second one. If you look, you don't want to do any of that modern physics stuff. Why did I just hit that button right there? The one I want you to look at is a little easier. You do it pretty much the same way, but just illusion it's righter. And I'll help you out with a free body diagram here, since first time stuff. Luge comes to the vertical part, from the vertical part, actually the angled part from up at a high distance, gets to the very bottom of the luge run though, and is moving, okay, that way. And it has an initial speed of 37 meters per second. And then when it hits the horizontal part right here, it stops. So it comes to rest. And you know what the acceleration is. The acceleration must be that way, and it's 2 meters per second squared. And so what I need you to do is figure out what's the required force, what's the distance the thing travels, what work was done by that required force, looks like friction to me, and what's the change in kinetic energy. And I'm not sure that the order I've asked those questions is the best order. You might decide to get D first because you know what the initial kinetic energy and the final kinetic energy is, because you also know the mass. So you can work it backwards as well. All right, we got about, I think, just about 2 minutes to go. So I'm going to let you go. You can work on it. I'll be hanging around here for office hours. You don't have to do problem 2. We'll talk about problem 2 on Monday, but I do want everybody to give a shot at problem 1 here. And you got a few minutes now to get it started and upload it by Monday. Last chance for questions. I'm going to stop sharing my screen with you. If not, if you want to wait and do this problem later on, have a great weekend. I hope don't eat too much candy. Everybody else, I'll be hanging around here and I'll be back at 10:30.
Thank you. Have a good weekend.
Too.
I have a quick question.